Howdy! Welcome to Elementary Statistics. I am Ms. Curtis, and I will be your instructor for this lecture covering Section 3-3, Measures of Relative Standing and Box Plots. In this section, we're going to talk about the Z-score, which is a very important statistical concept. You're going to be saying this over and over again. Percentiles, quartiles, 5-number summary, which then leads us into box plots. So let's dive in. Key concepts in this final section of Chapter 3 are to introduce measures of relative standing. So we've looked at measures of center, we've looked at measures of variation in order to describe distributions of data, and now we're going to take a look at measures of relative standing. These are numbers that show the location of data values relative to other values within the data set. Measures of relative standing can be used to compare values from different data sets or values within the same data set. And the most important of these is the Z-score, as we'll get into momentarily. There are other measures of relative standing, percentiles, quartiles, and those come together to form what's called a box plot, which we'll get into later. But first, let's dive into talking about the Z-score. A Z-score, which is a type of standardized value, is a number of standard deviations that a given data value x is above or below the mean value. So instead of listing a data value for the value that it is, we want to know where that data value appears in the range of data values throughout the distribution. So how close to the mean, how close to the tails, where exactly is this data value relative to all the other data values in our data set? This is where the Z-score comes in, because basically what we do is we convert the data value into the number of standard deviations that data value resides away from the mean value, and then that gives us a clue of where we are inside the distribution of data values. We can calculate Z-scores for both samples and populations. So the sample Z-score will be calculated by so x is the data value of interest. We're going to subtract from it the mean value x bar and divide it by the sample standard deviation. This converts it into a Z-score, which is the number of standard deviations that data value is above or below the mean value. Population Z-scores are calculated in a similar fashion. We just simply exchange sample statistics for population parameters. So we're going to take the population mean, subtract it from the data value, and then divide by the population standard deviation. Now the convention with Z-scores is to round them to 2 decimal places. And in all my experience in industry, I have never seen Z-scores reported in any other way. They've always had 2 decimal places with them. So while you look at the graphic there on the right, and you see that Z-scores are given in whole numbers. This is just for illustrative purposes, to illustrate that the Z-scores correspond with standard deviations. When we're actually reporting and using Z-scores for real-world purposes, I've never seen anything but Z-scores reported with 2 decimal places. How do we interpret the Z-score? Well, a Z-score less than the mean is always negative, and a Z-score greater than the mean is always positive. So a negative Z-score means that our data value resides to the left of the mean value. The mean value, the value in the middle, always has a Z-score of 0. So then, if the Z-score is negative, we know it's to the left of the mean value. If a Z-score is on the right side of the mean, then it's going to be positive. So just by looking at the sign of our Z-score, we know which side of the distribution we're on. The empirical rule that we discussed previously also applies to Z-scores. So ordinary values that we would ordinarily expect to see in a distribution, especially if that distribution is normalized, then we're going to look for Z-scores between 2 and -2 inclusive. Unusual values will either be Z-scores above 2 or below -2. For example, would a pulse rate of 48 beats per minute be unusual if the mean pulse rate is 67.3 beats per minute and the standard deviation of 10.3 beats per minute? So we have the mean, we have the standard deviation, and we have the value of interest, which is the 48. So we have everything we need to calculate a z-score. So let's calculate the z-score. So we do that by looking at the definition, x minus x bar over s. 48 is the value of interest. We're subtracting from the mean, which is listed here in the problem statement, 67.3, and then dividing by the standard deviation. Punch all that out, and we get negative 1.87. That means that this value of 48 is located 1.87 standard deviations to the left of the mean value. But the question is, would this value of 48 be unusual? And we have to answer, no, it's not unusual because it's within 2 standard deviations from the mean. So because it's within this central region right here, it's within the 2 to negative 2, then we're actually saying that that's going to be a value that we would expect to see. It's not unusual. Let's take a look at our presidents of the United States and what a z-score would be for a U.S. president who had a height of 190 centimeters. First, we need to calculate the mean and the standard deviation. You cannot get a z-score until you have mean and standard deviation. So let's get those out. We're going to go into StatCrunch, and we're going to go through, and we know how to do this, or we should know how to do this. And we're going to get, here in our results window, we have the mean and the standard deviation for our height data points. So now we're ready to calculate z-score. We use the definition of z-score to calculate it. So the definition of z-score is x minus x bar over s. We're now going to put in the values that we have. So the 190 comes from the problem statement. This is our data point of interest. So that's going to be our x. The 179.68 is our mean value. It comes from our results window in StatCrunch. The 7.31 is the standard deviation, which we get also from our results window in StatCrunch. Punch that out and you get 1.41. This is our z-score for a president that has a height of 190 centimeters. How many standard deviations is this? I'll give you a moment to figure that out. Or you can guess if you want. I mean, I don't really know the difference because I'm not in your head. Okay, well, I hope you said 1.41. That is the definition of a z-score. Z-score is the number of standard deviations a data value is from the mean value in the data set. Should a U.S. president who wants to be taller want a higher z-score or a lower z-score, and why? Again, I'll give you a moment. Okay, so if you want to be taller, then you're going to want to move to the right of the mean value. You're going to have a value that's greater than the mean value. So you're going to want to move to the right of the mean value, and therefore you would want a higher z-score because you're moving farther to the right in your distribution. Let's talk for a moment about percentiles. Percentiles are simply measures of location. There are 99 percentiles within a data set, and they are denoted with a capital letter P and a numerical subscript that indicates the percentile that we're talking about. So P1 is the first percentile, P2 is the second percentile, all the way on to P99, which is the 99th percentile. In essence, when you see a percentile, what you're looking at is the area under the distribution curve as you go from left to right. So let's say we have here a distribution of our data values. And imagine this to be something like a histogram or a frequency polygon, where we've connected the tops of all the columns for our data sets. It makes this wonderful little normalized bell-shaped curve. And let's say we want to look at this x value right here. So to get the percentile, what we want to look at is all of the data values to the left of that value of interest, that x. So everything that's less than the x is what we want to include in the percentile value. So then we're going to take the number of values that are less than x, we're going to divide it by the total, and that's going to give us a percentage. But if you look at the graph, what that really is a percentage of the total area under the distribution curve. So if this area here is, say, 89%, then that means our x value here is in the 89th percentile. Let's look at an example involving chocolate chip cookies. And yes, I love chocolate chip cookies, which is why I keep coming back to them. So here we have a data set of 40 chocolate chip cookies, and we counted the chocolate chips in each one. We're asked to find the percentile for a cookie with 23 chips. The first thing you want to do when looking for a percentile is make sure your data set is organized and sorted from lowest to highest. This makes it easier to actually figure out what the percentile is. Fortunately for us, this data set is already sorted. You can see it starts here from 19 and goes up as you go from left to right, and then the next row, the next row, and the next row. So first we want to find the percentile for 23 chips. We're going to have to look for the first 23 in the data set after it's sorted. So here's our data set that's sorted. We're going to look for the first 23. And so we have to find the count for the number of cookies that are less than 23. That's why we're looking for the first 23. So the first 23 we see right here. So now we need to count the number of cookies that are less than 23 chips. So we start here with this one. This 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we've got 10 cookies that have less than 23 chips. So we're going to say that the percentile of 23 is going to be 10 divided by the total number of cookies in our data set. That's 40. And then we're going to multiply that by 100. When you punch that out, you get 25. Therefore, we know that a cookie with 23 chips is in the 25th percentile. We can use StatCrunch to calculate percentiles. Now, percentiles are not directly calculated in StatCrunch, but the advantage of performing percentiles in StatCrunch is that StatCrunch makes it easy for us to sort data sets that aren't sorted and then to do the counting and make it very simple. Let me illustrate with the chocolate chip cookie example we just looked at. First, what you want to do is place your data into StatCrunch. Next, make sure your data is sorted. In this case, the data is sorted. So we're starting from the lowest value and we move our way on up all the way to the highest value in our data set. Once the data is sorted, we want cookies with fewer than 23 chips because we're asked to find what percentile a cookie with 23 chips is in. So we're going to look at the row numbers on the left side of our data sheet, and that's going to tell us what the numbers we need are. So first we find the first occurrence of 23. That's right here. Then we're going to look at the row number directly above the row with that number. So that would be a 10 because the first 23 is in row 11. So we're going to go one above. That's going to be the 10. So there's our first number, 10. And then we look down at the bottom to get the total number, and that's 40. And now we've got what we need to calculate our percentile. So we calculate it just as we did before. Take the 10, divide by the 40, multiply by 100, and we see that we're in the 25th percentile. So StatCrunch can make this process of finding the percentiles a little bit easier. What do we do if our data isn't already sorted? Well, let's look at an example to illustrate. Let's go to our Presidents of the United States files, and clearly the height of the Presidents of the United States as they served in office is not sorted from lowest to highest. So we're going to have to do that to figure out what percentile a U.S. President would be in with a height of 171 centimeters. So first, let's go get our data set. And once our data set is in StatCrunch, we're going to go up and we're going to click Data and then Sort. Once we do that, we get this options window that comes up. So we're going to select the column that we want to sort in. The direction for the sorting can either go from lowest to highest, which is the default setting, or it can go from highest to lowest, which is descending. You always want to select ascending, so make sure that the default value is there selected, and you just let that be what it is. Finally, you want to click in this options down at the bottom of your options window, this checkbox for open in a new data table. The reason why you want to check that box is because if you don't check the box, that will sort the data right there in the table, and you might end up, messing things around. So I just like to just check that box, put it in a different table, so I leave my original data set the way that I found it. I don't have to worry about anything getting messed up. Once I go through all that, I click Compute, and out comes my data, and it's sorted in a brand new table. Look at this. I don't have to do anything. So now I can just grab my numbers like I did with the previous chocolate chip cookie example. The number of interest is 171. So I'm going to look for the first instance of 171 in my data set, and it's right here. Then I'm going to grab the row number directly above it. That's the 5. Go down to the bottom to see the total in my data set, which is 38. And now we're ready to calculate. So total number of data values below the value of interest is 5 divided by the 38. And then I'm going to multiply by 100, and that gives me 13.2%. Therefore, a president with a height of 171 is going to be in the 13th percentile. Notice that when we get a decimal value out, we're just going to round to the nearest whole number. So 13.2 rounds down, and that's where we get the 13th percentile. So you can see that StatCrunch can make this percentile thing much simpler. Even though it doesn't calculate the percentile directly, it would be nice if it did. They could easily program a function into the menus there to where you could actually just select the menu option and then just say, give me the value of interest for this particular data column, and then boom, it just pops out the number right there in the results window. Unfortunately, nobody's actually done that, but the methodology that we have, a sort of a crutch method, it's not too bad. It's actually simple once you get the hang of it. Let's talk for a minute about quartiles, because percentiles can range anywhere from 1 to 99, but there's some percentiles that are of greater interest than others, and these are the quartiles. So quartiles are simply measures of location that divide a data set into 4 groups with about 25% of the values in each group. So what we're looking at are the 25th percentile, the 50th percentile, the 75th percentile, and then, of course, the largest value there on the end, the so-called 100th percentile. So the first quartile, symbolized with Q sub 1 or Q1, separates the bottom 25% from the top 75%. So here we've got the bottom 25% in our distribution, separating it out from the top 75. Q2, which is the second quartile, separates the bottom 50% from the top 50%. This is the same as the median value. Think about it. 50% on the top, 50% on the bottom. So the value that's there in the middle is the second quartile. But that by definition, it's the value in the middle. That by definition is the median. So the second quartile is the same as the median. Then Q3, the third quartile, separates the bottom 75% from the upper 25%. There are several statistics that involve quartiles. For example, the interquartile range, or IQR, is simply the third quartile minus the first quartile. And if you look at this, this is roughly 50% of the data that's roughly in there. So not quite one standard deviation, because remember from our empirical rule, it's about, 68% of the data lies within one standard deviation. So not quite the one standard deviation, but a little bit close. There's the semi-interquartile range, which is just half of your IQR. There's the 10 to 90 percentile range, which is the bulk of the distribution. And then there's the mid-quartile, which is simply the average of the third and first quartiles. The IQR has, I've actually seen that in some places. The others I really haven't seen that much use for, but they do pop up from time to time, depending upon which circles you're actually running in. All of this brings us to what's called a 5-number summary. So we can take these relative measures of standing and we can put them together into a summary that will give us a brief description of our distribution. So this 5-number summary starts with the minimum value, so the one that's here on the far left side. Then we go to the first quartile, the second quartile, which is the same as the median, the third quartile, and then the maximum value. These 5 numbers taken together provide us a 5-number summary of our data distribution. They are together known as a 5-number summary. Go figure. Let's take a look at how this actually plays out. So what's the 5-number summary for the heights of U.S. presidents? So if we go to Stat and then Summary Stats and Columns, then we can look in the options window that pops up, select our data set, it's here in the height column, and then we can select our, our statistics here that we want to calculate. Note that I'm actually selecting them in the order that the 5-number summary goes in. Typically when you're asked to solve problems for a 5-number summary, you're being asked to provide the numbers in the conventional order. So first you're going to calculate the minimum, then the first quartile, then the median. You want to look for Q2, but just remember Q2 is the same as the median. So when you don't see Q2 listed, don't think, oh my gosh, I can't calculate it. No, it's the same as the median. So min, Q1, median, Q3, and then max. These numbers here will give us our 5-number summary. When we press compute, out pops our results with the 5-number summary in the conventional order, and so all we have to do is just transfer the numbers over. This brings us to the topic of box plots. So box plots, also known as box and whisker diagrams, because it looks like a box with whiskers on each side, is simply a graphical representation of a 5-number summary. So instead of listing the numbers in a table, we can actually list them with a visual representation, and that visual representation is the box plot. So essentially we have a box here that corresponds with the inner quartile range. So the left edge of the box is the first quartile, Q1. The right edge of the box is the third quartile, which is Q3. We draw a line in the middle of the box to symbolize Q2, or the median value. The whiskers come out from the edge of the box, and on the left edge is the minimum value, on the right edge is the maximum value. So depending upon where these lines are with respect to each other, we can get a graphical view of the data set and how it's distributed within the data set. This allows us to identify properties such as skewness with very great ease, because a skewed data set will mean that this box and this line here in the middle representing the median will be shifted to one side or the other. Whereas if this is more centralized, then we know we have something that approximates a normalized distribution. So the more off-center the box is on the line, the greater the skewness in the distribution. we can actually add outliers into what are called modified box plots. So an outlier, as we know, is a value that lies very far away from the vast majorities of the other values in a data set. We've seen how outliers can greatly affect the mean and the standard deviation of a distribution. An outlier can also dramatically change the scale of a histogram and thereby obscure its true shape. Outliers can also have an effect in the box plot. So we can modify the box plot. So instead of drawing the whiskers with an N that's representing the maximum and minimum value, what we do is we draw the line out to the extent of the expected values, or the what you would call the usual values. So plus or minus 2 standard deviations from the mean. Then all the values in the data set that are beyond that are what we call unusual values. These are the outliers in our data set, and they're marked with dots or stars or X's, as you see here. Modified box plots therefore separate out the outliers in the presentation. They give you a sense of everything that's in the data set, but if you want to ignore the outliers, this visual representation helps us to do that without necessarily excluding the outliers. So in modified box plots, outliers typically have to meet certain special criteria. They have to be above Q3 by more than 1.5 IQR, or they have to be below Q1 by more than 1.5 the IQR. Let's look at an example of making a box plot, again with our Presidents of the United States files. What would a graphical 5-number summary of our POTUS data look like? Remember, the box plot is simply a graphical representation of the 5-number summary. We can make box plots in StatCrunch. We just go to Graph and then Box Plot. Once we do, we get this dandy options window that pops up. So we're going to select our data set, and the height is what we're typically looking at. So we're going to select that. And then notice down here under Other Options, we're going to check a box for Draw Boxes Horizontally. I don't know why this isn't the default setting in StatCrunch. Most of the box plots that I've ever seen throughout my tours in industry have box plots drawn horizontally. There are certain circles, however, that prefer drawing the box plot vertically. And for whatever reason, the people that designed StatCrunch decided that that was going to be the default setting. But typically, you're going to see box plots drawn horizontally. So checking that box is a really good idea. All the other default settings are great for us. So then we're just going to come down at the bottom and click Compute. And then we'll get a results window that you see here. Now, notice how scrunched up the box plot is. And so we can actually resize the window. If you put your cursor on the side of the window, it turns into an arrow, and then you can actually drag it out so that you can actually get something that looks more reasonable proportionally. And this actually makes it easier if you're looking to identify, say, a question on a homework assignment that asks you which of these box plots represents the data set. Well, it's kind of easier to make comparisons if you have the box plot stretched out a little bit more than what naturally comes out from the results window. So just be sure to grab that edge of the window and extend it out to where you need it so you can make the comparison you need to make. At this point, let's take a moment to step back and consider everything that we've done, because where we're at now is the end of the 3rd chapter. So we've come quite a ways here, and we've actually been discussing several basic tools that are commonly used in statistics. So we've been busy establishing the foundation for further statistical analysis. We've come to understand the importance of the context of data. We need to know where our data is coming from. We need to know how we're getting our data, because how you sample the data has a great effect as to the data that you're going to get and the results of your analysis. We've looked at measures of center and variation. We've looked at distributions, whether or not they're normalized, and the effect that outliers can have. We've looked at how patterns can change over time. And we've looked at making conclusions from our data, and extracting from them the practical implications of our statistical results. So you think about it, we've actually started to gather quite a few tools into our statistical toolbox. But just like any other tool, it can be great and do one fantastic job, but it can never replace good old-fashioned thinking about what the tools provide. Remember that at the end of the day, statistics is really about critical thinking. And so you need good judgment and critical thinking skills in order to correctly interpret and make conclusions from the results of our statistical analyses. That brings us to the end of this lecture. If you have any questions, you know how to get a hold of me. Otherwise, I will see you in the next video. Thanks for watching.